Okay, we're going to really start by exploring right triangles and our trig ratios, making sure we understand them well. So I have A, B, and C that I'm going to put out here and create this right triangle here. Okay, I construct it so that I know it's a right triangle. Save a little bit of time for measuring. So let's consider angle A. Okay, let's just think about angle A for a minute. This way. There we go. Angle A has a measure, in this case 36.87 degrees. Let's measure our lengths, and we can kind of see them, but I'm going to just hit the length of that side and the length of this side. So this is 3/5. So our sine of 36.87 is equal to 3/5. So let's put that in there. What is the sine of a 36.87 degree angle? And hit enter, and I get 0.6001, which what I just said was 3 divided by 5, and that is 0.6. There it is again. So why is it slightly off from this? Because that's a rounded number. That angle measure, they rounded that. It's probably 0.8699 something. Okay, because it's pretty close. It's pretty darn close. So the ratio here is 3/5. That's exact. The angle is the one that's been rounded. The exact ratio is 3/5, which is 0.6. Now, let's consider for a moment, I'm going to change actually this so that this triangle shows up in a different color. There we go. We'll make it green. Okay. Now let's consider if I place let's place point D at 2, 0. Okay. And now we can form a triangle ADC. ADC. Now, what has changed about A? Is its measure still not 36.87? So what's changed about A is what? Now think about that for just a minute. What's changed about A is what? It is part of, right? It is part of, let me hit escape here. It's part of two different triangles. One was a right triangle, so the ratio was easy to figure out. But what if I have a triangle? I'm going to just take, actually what I'll do is just take this triangle off for a second. Oh my gosh, I am just struggling here. Here we go. What has changed about A, right? It's still the same angle it was before. It's just now not part of a right triangle. So does that mean it doesn't have a trig ratio? Does that mean that we can't figure out its sine? Well, it turns out that we know that it would have this sine that's a ratio of 3/5 if it were put into this triangle with a length of 3 and a hypotenuse of 5. And what if we dilated? Let's dilate that other triangle. Let's put it back here. Let's take away this triangle for a second. And let's try doing a dilation. Okay, so we're going to just click off the side. Here we go. A dilation of this triangle by this point and a factor of 2. So now, what has changed about the angle? Nothing's changed about the angle. We said that we know it has a ratio of 3/5, but now it doesn't have a ratio of 3/5, does it? Well, dilations, what do? One of the things they do is they preserve proportionality. So we see this one is not 3/5, but indeed it is 6/10. And wait a minute, 6/10 is 3/5. It's just been doubled. So in other words, it doesn't matter which triangle I pick to make this angle a part of, it's always still going to have that same ratio for sine. So here's my point. Ready? Angles, their ratios, their trig ratios like sine, are actually really just kind of a property of the angle. You can think of them as a property of an angle. And therefore, if I construct an angle even that's not a part of a triangle, and if I just made it a 36.87 degree angle, and I constructed it, let's try doing that. So B is to E prime, and E is to E. And we know, because I just constructed this, these angles here, this angle here is not part of a triangle at all. Yet it carries with it the property that its sine is 3 over 5. Its sine is still going to be 3 over 5, even though it's not even a part of a triangle. So this is very important, because if we go back to, let's take this triangle, where was it? Right there. If we only looked at that, oh boy, here I'm doing goofy things here. If we only looked at this triangle, right, then it doesn't matter that it's not a right triangle. So this is important. I want you to remember this. Non-right triangles have trig functions for their angles anyway, because trig functions, we're going to now stop thinking of them exclusively as ratios of side lengths and start thinking of them as ratios that are unique to angles. They're unique to angles, even if they are not part of a right triangle. So that's the first major thing to consider and be aware of. And now we're going to start something new. I'm going to show you something else. What about, now this is obvious, right? I can figure out the sine of this angle just pretending that it was part of a right triangle, and I would know this is the opposite, and that's the hypotenuse. But what about if I had to find the sine of this angle? What I mean by that is, instead of an acute angle, one that's less than 90 degrees, what about an angle that's more than 90 degrees? Let's plot one out. So if I said, okay, angle A, again, we're going to put that at 0, 0, right? Angle B, we're going to also put that one right where it was 4, 0, I think. And then let's place angle C at, -2, 3. And we form that triangle. And let's do that real quick. Now, this is the largest angle, angle A, right? So if I measure angle A now, hey, what happened? Let me hit escape there. Where's point B go? All right, let's try this again. B, A, C. So now we have an angle that measures 123.69 degrees. So how can we do opposite over hypotenuse? Remember, hypotenuse is always the longest side in a right triangle. If I continue these legs forever, we'll never get to a hypotenuse, right? Because it'll never be, this can't be part of a triangle with a right triangle, with a 90-degree angle in it. Remember, there's only 180 degrees inside of every triangle? And if 123 of them are in this angle, which is not a right angle, there's not enough left for another one to be a right angle. We cannot make a hypotenuse, because a hypotenuse by definition is opposite, is the side of a triangle opposite the right angle. So since there is no right angle, there's no hypotenuse. And opposite over hypotenuse would just say take the length of this over, we can't do it. So the bottom line is it cannot be done, right? Cannot be done. Well, actually, mathematicians don't like that kind of answer. So what they do is they say, let's come up with another way to do this. Let's put in here a point D. So D equals, and let's say, could we construct a right triangle with the supplement of a, so every obtuse angle does not have the ability to have a right triangle, but it has a partner angle, which is its supplement. That's the angle. Now, why is that not selecting? Sorry. You ever get frustrated with this stuff like me? I'm sure you do. Does not want to click there. I don't know why. I'm going to start this again. Here we go. Let's make a regular polygon. You can use these points over here if they ever frustrate you. A, C, D, C. No. I don't know. I don't know what happened. Mr. T is frustrated, and I'm not gonna. Oh, wait a minute. That's a rigid polygon? I don't want that. I got the wrong tool. So that's usually the problem there. It's not the tool, it's the guy using it, and he picked the wrong one. All right, so sorry about that. Let's get back on track here. Every obtuse angle has a partner angle, which is an acute angle that is its supplement. Now, if you look at these two numbers and you add them together, you're going to get 180, right? It doesn't matter if I change, oh boy, that was not intended. If I change C and I move C somehow, it won't matter. Okay, I can move C, and this angle and this angle are always going to form 180 degrees because they're a linear pair. So what do? How do we find a trig ratio for this angle? What we do is we just use the trig ratio of this one. So if we want to have the sine of this, it's going to be equal to the sine of that. Let's take a look at our calculator and let's figure that out for sure and confirm it. So here I have a 123.69 degree angle and a 56.31. So let's measure what is the sine of a 56.31 degree angle. So we enter that and we get 0.832051. How about what is the sine of a 123.69 degree angle? So what is the sine of a 123.69 degree angle? And we have exactly the same sine. So they share a sine. They share a sine. Well, let's think about this some more. Would they share a cosine? So let's try the cosine. So we go trig cosine. What is the cosine of a 56.31 degree angle? Oh, that's great, 55. So we're pretty sure, let's try cosine. What is the cosine of a 123.69 degree angle? Okay, wait a minute, there's something different there. Can you see that? These are not the same exact numbers. They're very close. Do you see this little thing right there? That negative sign? The cosine is negative, so it's almost like the cosine of its supplement, but it's negative. Why is that? Well, let's think about it. The adjacent side of this angle here, 56, it goes, now we're going in a negative direction from our original. So if we have an obtuse angle, our adjacent -2 over this length here, which was, what's this length here? I don't know. AC would be that one right there? No. It's this one right here, 3.61. So we have -2 over 3.61, but -2 is a negative number. So in other words, because it's part, we know that this side actually doesn't really exist, and it goes in the opposite direction of the angle of the side of one of its sides. Like this is the ray that makes up the side right here, right? So this ray is going in the opposite direction of the ray. So we're using an opposite direction measurement to construct this triangle. So therefore, we're going to end up with a negative cosine. Is that true for all supplements? Well, let's try like 120 and 60. So if I take the sine, I'm just exploring just a little bit more, sine of 120 and the sine of 60, and we get the same exact values, okay? There's the same exact values. What about the cosine? If I take the cosine of 120, I get a negative value. Cosine of 60, that is its complement or supplement. That is its so the acute angle has a cosine that's positive, and the obtuse angle has a cosine that's negative. That's important to know. All right, how about tangent? Let's just try that out. Tangent of 120, and that one is negative also. Why would that be? Well, tangent is opposite over adjacent. Opposite is a positive number, but the adjacent is going to be a negative number. So this is important to know, okay? And I want you to keep that in mind as you think about triangles and angles having a property. Even obtuse angles have properties, but sometimes their cosines and their tangents, those ratios are going to be negative. In the case of cosine and tangent, they're going to be negative. Okay, now we'll see how we can use this information.